University of Evansville. My advisor has been Dr. Jan Fion, and my mentor has been Corey Rice. My presentation is Magnesium zinc oxide via atomic layer deposition. So, brief outline of my presentation. I'm going to be going over background and motivation, atomic layer deposition, the film that was deposited, and its optical and structural characteristics, as well as its electrical properties, the deposition rate, becoming Telluride deposition, and conclusions. So, cadmium telluride solar cells. So this is an image of what most of the basis of cadmium telluride solar cells. And then there's also an image of how they work. So basically you'll have light coming in, and it will hit your window layer, which is your N-type semiconductor. In this case, it's cadmium sulfide. And then it will go through to your absorber layer, cadmium telluride, and it will create an open circuit voltage. So cadmium telluride cells are common in commercial use because of their low production costs. So what we want to do is, instead of using cadmium sulfide, we're going to use magnesium zinc oxide as the window layer, and that will also eliminate the need for a highly resistive layer. So another group has done this before, and they've noticed that magnesium zinc oxide will have a higher efficiency when put into the full solar cell. So previously they deposited the film by sputtering, and we chose to use ALD. So the reason MZO has a higher efficiency, so type 1 is what MZO would be. So as you can see, the band aligns better with the cadmium telluride. And so in type 2 would be like your cadmium sulfide and cadmium telluride. So the bands don't align as well. And what that means is you'll have less chance of recombination. And so with like MZO, you'll have a higher voltage from that. So ALD. Basically, you'll have your substrate, and then layer by layer, you'll have deposited zinc and magnesium. So there's more variation of layers you can do with this. It also creates a very uniform film. So the film itself. We chose to use 6 different layer ratios to test. So what we're looking for is the group before Kephart from Colorado State University found that their best film was 23% atomic magnesium. So that's what we were trying to match. So as you can see, I have an example of what each film, what each layer ratio means, and also what is happening in the ALD. So it'll deposit water, magnesium, water, and zinc, and it will repeat that or vary that. So what we did is, after we characterized each film, we annealed each film to the same parameters it would undergo in a closed space sublimation cathode deposition to see what the effects of the film, the effects it would have on the film. So we used a scanning electron microscope to look at it. So these are as deposited and after annealing. And side-by-side comparison. So one thing to notice from this is that the grain sizes do vary quite a bit. Also, you can't really tell in this, but after annealing, the grain sizes do get larger, and that's where the error bars are because of the different grain sizes. So another way you can look at grain size is from the XRD, and it's another way we use to characterize the film. So as you can see, it does appear that after annealing, even in the XRD, the grain sizes do enlarge. That's what we would expect. And the reason you'll have variations in XRD and SEM grain size is because with the XRD, it's measuring grain size by all of the defects it finds, whereas SEM, we're just measuring from the picture. So more XRD. So the top image is a phase fitting, and so what we did is we have the raw data, and then the XRD will fit a phase to that data. And so what we found is that all samples had the same hexagonal phase, which, I mean, it can vary over MZO, so it's interesting that it's all the same phase. The graph down here shows before and after annealing. So what we see is after annealing, the film seems to become more crystalline, and that's what the peaks mean. Also, each film exhibits an amorphous hump at the beginning, that's what that is. And that's probably from the glass, because these films are so thin that even at a 1 degree angle instance, you're still going to see some of the glass. So more XRD. Lattice mirrors, like I said, they all have a hexagonal space group. And so you can see that the parameters A and C are labeled on there. They're also labeled in the image above to get another picture of what these mean. So what we found is the last parameters don't really seem to change with annealing. They do ever so slightly, but really if you put it on a scale in angstroms is 10 to the -10th meter, so they really don't change much. So another one we used to characterize these films was UV spectrophotometry. This is the data you will get raw from the machine, so you'll get a transmission and reflection curve. And from that you can calculate the band gap. So this has been studied before for MCO films, and this is what you would expect that with a higher magnesium concentration, you have a higher band gap. MgO is about 7.8 eV, and zinc oxide is about 3.3 eV, so this is what you would expect, that combination. Also note from this, after annealing it appears that the data fits a better linear trend line, which is what you expect because with annealing you'll have a more homogeneous film. So electrical properties, this is the Hall effect and 4-point probe data. So what you can see is that after annealing, the carrier concentration and mobility go down, which is what you would expect. Also, the sheet resistance and resistivity go up after annealing. So EDS, this is a data you can get from the scanning electron microscope. And this was important in identifying which one of our films was closest to the reported 23% atomic magnesium. So what it was found that the closest one was the 3 zinc to 2 magnesium layer ratio, and it's about 21% atomic magnesium. Deposition rate. So also reported in the Kephardt's dissertation that they used a 50 nanometer film. That was their highest optimal film. So from this we can get how many cycles per thickness, so we can tell how many cycles to get the 50 nanometers for. So results, band gap, one thing I haven't noted yet is the band gaps. So Kephardt reported a 3.7 eV band gap. We found about 4.1 eV. He also noted the sheet resistance was above 10 to the 7th ohms per square, and we found to be 9.15 times 10 to the 7th ohms per square. So the rest wasn't reported, but this is what we found. So after we deposited the MCO film, we deposited cadmium telluride onto that. And there's 2 ways we did that. One was sputtering, and the other was closed space sublimation. Then the film would go through a cadmium chloride treatment, and then be annealed at 390 degrees Celsius. And then copper and gold would be deposited to create the back contacts like you can see, and then be annealed at 200 degrees Celsius. Also around the edges is indium, and so what that'll do is that'll allow the electrons not to travel so far, so you'll get a higher voltage. So these are the 2 differences between the 2 depositions. So with sputtering, it occurs at a lower temperature, but the deposition time is 2.5 hours. It's also at a lower pressure. The closed space sublimation, that's how we annealed the films to begin with, to see what happened to them in this sort of deposition. So it's at a higher temperature, but it's very quick, and it has a torr and a pressure of 50 torr. So in the future, we're going to be investigating optimizing these film parameters because so far we've tested a few of the devices and they don't have the high efficiency that we'd be expecting. So we're still looking into that. So we can vary the ALD parameters. Right now the films are deposited at 150 degrees Celsius, so we can vary that. And so we can also explore properties in MCO after annealing air. My references? Any questions?
Yeah, where did you do a lot of the characterization at, right? In R1, or was it?
Yeah, it was mostly in R1. There's also in the other engineering building, so the SDM and XODR.
Oh, okay, okay. That equipment at first is a little overwhelming, isn't it, when you sit down and sit in front of it? What did Corey sit with you when you first started?
Yeah, he
to analyze the different films. Is there any question? Yeah.
So, as someone non-EV, and maybe this is more of a material science question, but you say you put the layers of water, zinc, and magnesium down, and you're doing that at 150 degrees Celsius?
Yes, that was what was deposited into the chamber, yes.
So when you deposit water and then cool it down, say you have a layer of water, and then when you put the next substance in at 150 degrees Celsius, do you evaporate the previous layer?
Oh, yes, it is evaporated, yes.
Okay.
Yeah. Sorry, I forgot to mention that.
Maybe you can go into a little bit more detail about how the ALD process works. That might clarify the question. At your previous slide. Yeah. So describe what's going on in each one of those, correct? Or schematic.
Yes, so in each one, there's just like a pulse of, so if you, like say the blue is zinc, so you have like a pulse of zinc into the chamber and then it's evaporated out, and then you'll have a quick pulse of water and then a pulse of magnesium.
So what's the purpose of the water? This is the question.
Oh, so what that's doing is that's like creating your,
The oxidizing.
yeah, yes. Yeah, so it's creating your like, yeah, it's oxidizing, yeah.
So and then the hydrogen just goes away, or any excess water in hydrogen goes away.
Yeah, it's,
I had a question. You had a slide showing before and after milling, and didn't have time to study it.
this one or which?
No, it was a chart, it was a table showing the resistance and sheet resistance
Oh.
and things like that before and after. Oh, maybe that was it, yeah. Was it the next slide we got here on the table? No, I guess it was that one, okay. So after annealing, the carrier concentration goes down. Mobility goes down. So you want a high resistance, right?
Yes.
So I just don't quite understand why the sheet resistance goes down after annealing. But maybe it doesn't change that much. Oh, it goes up rather, yeah.
Yeah.
Yeah, so I don't understand why it goes up after. Because, I mean, if I think of resistance due to defects and grain boundaries and things like that, then that would go down, right? When you anneal, because you have less grains.
Well, you'll have larger grains, so yeah, that would reduce the, I'm sorry, that would increase the resistance.
Larger grains increases the resistance. That's the way I understand, because I think if the grain boundaries is closing the resistance. I obviously don't understand.
Well,
So I would think after annealing, you have larger grains and less grain boundaries. So if the resistance is due to your boundaries, you would have less resistance because you have less grain boundaries. But obviously, my understanding is wrong because it's not due to grain boundaries.
So instead of focusing on how the morphology changes with the annealing, think about how the change in the carrier concentration and mobility that you observe would affect the subsequent resistance values. So you see that the carrier concentration is going down several orders of magnitude after this annealing. And so since resistance in general is a product of carrier concentration and mobility, by having one of those go down by several orders of magnitude, the resistance should also.
Yeah, that would make sense. So I guess my interpretation would be that you're getting rid of defects that increase the carrier concentration.
Actually, what we strongly suspect is that as deposited, it's not a purely stoichiometric film. It's not fully oxidized. And so you can have some interstitial metal that might be there, some zinc, for example, that might be adding carriers.
Oh, I see.
And so increasing that carrier concentration and making it more conductive. When we do the annealing, it completes the oxidation and it brings the carrier concentration back down to something you'd expect from intrinsic metal.
Oh, okay. Okay, that makes sense.
Yeah.
But there's no change in the resistivity. So resistivity is the bulk resistivity, right? Sheet resistance is what happens when you put
No,
electrodes.
the bottom one shows it too.
Right, and there's no change.
There's several ways of magnetism.
There's a huge change between purple and red.
So down at the,
Is that
See that?
Oh, way down.
Yeah, it's way down
That's
there,
how the-
yeah.
Yeah, okay. So it's about the same as the sheet resistance.
well, let's thank Gary again.